I'll start this video by doing a couple of simple problems. These will be easier than the first free fall problem that I did the other day. Start with a physics instructor on vacation is on a bridge over a river, wondering how high above the river he is. He drops a rock in the river and times how long it takes to fall by counting 1001, 1002, 1000, ... He arrives at a time estimate of 3.5 seconds. How high above the river is he? This is based on an actual event. Anyway, let's start with our free fall equations. We know that they'll apply here. So we have y equals y naught plus v naught y t minus 1/2 gt squared. This one has a minus sign because we're assuming up is positive, and I'm going to switch that here in a second. We also have, we won't need it I don't think, but we have v sub y will equal v naught y minus gt. Okay, I don't plan on using that equation for this problem. Let's see, if I use this, I can imagine, I'll make a sketch here. Got the river, we have this person standing above the river dropping a rock, or that's the bridge I mean, and then down below there's a river flowing along here, and the rock falls down there and hits that. Now we can assume or define y to be equal to 0 down here, and the initial height of the rock here, this will be y naught. Okay, and so with this assumption we can let's see, oh, also the rock is dropped, so y naught is equal to the height of the bridge actually. Or at least it's equal to the height at which the person drops the rock. Let's see, v naught y will equal 0 because it says drops a rock. When you drop something, its initial velocity is 0. If you throw it, it may not be 0, but dropping it, that'll be the case. We have y final down here at the river level is going to be 0. And so we can rewrite this equation. Well, first of all, with v naught y being 0, we get y equals y naught minus 1/2 gt squared. At the end, we'll have y is equal to 0. That's when it hits the water down there. So we have 0 equals y naught minus 1/2 gt squared, or y naught is equal to 1/2 gt squared. So this is a relatively simple plug and chug equation. I'm going to do it in an even easier way here in a second, but that's what we have. So the initial height that the rock was dropped from will be 1/2 times 9.8 meters per second squared. I'm only keeping two significant figures because I've only got 2 on the time there, if that. Counting 1001, 1002, etc., it's actually pretty hard to estimate half seconds doing that, but we'll go with it here. 3.5 seconds squared, and if you plug the numbers in there, you get that the height of the bridge is equal to 6.0 times 10 to the first meters. And I'm writing it that way because when you write numbers in scientific notation, you can easily show how many significant figures you have, because in scientific notation, a 0 after the decimal point is significant. There is that form of notation people sometimes use where they'll write a decimal point after that, but that's too easy to not notice. And so I don't really like that. Use scientific notation if you want to show the sig figs. Okay, let's also do this with down is positive and initial height equals y naught is going to be 0. Okay, now the equations change if down is positive. You have y equals y naught plus v naught y plus 1/2 gt squared in that case. We're starting at the origin in that case, so here's where y is equal to 0. We end up down here. We don't know the distance, but we do know, whoops, there's a v naught y t here. We do know that v naught y is 0, so we have 0 here, we have 0 here, so we just get y, the distance fallen, will equal 1/2 gt squared. Okay, and so you would just plug in the 3.5 seconds here and 9.8 meters per second squared, and you get it that way. Sometimes it is easier to pick down to be the positive direction, as it is in this problem. Here we have a dishwasher working at the observation deck on the Space Needle. I don't know that they have dishwashers on the observation deck, but pretend they do. Of the Space Needle in Seattle, somehow drops a handful of forks over the edge. An alert tourist sees the forks leaving the dishwasher's hand and screams, "Falling forks!" The observation deck is 160 meters above ground level. If the tourist manages to finish yelling "falling forks" within 0.90 seconds of the release of the forks, who's measuring this? Anyway, how long do the people on the ground have to get out of the way before the forks hit the ground? This is a similar problem. Okay, so we've got the Space Needle here, kind of shaped roughly like this. Okay, and it's got the needle on top. Anyway, should we let down be positive right from the word go? All right, here's where y is equal to 0. Down is positive, so y is equal to 0. Here's y final down here, some distance away, which we happen to know it's 160 meters in this case. Now, our equation of motion, we'll only need to use the one on this problem. Y is going to equal y naught, oops, this is y naught actually, plus v naught yt, because down is positive, this will have a plus sign in it, 1/2 gt squared. And again, we'll have y naught is 0, v naught y is 0, so those two terms vanish, and I just get y final will equal 1/2 gt squared. Well, we happen to know that y final is going to equal 160 meters. Okay, so we can set that in here. The only thing we don't know is how long they're going to take to fall. So 160 meters. Oh, I'm figuring out how long they take to fall, and then I'll subtract that 0.90 seconds because they fell for a certain distance before the person finished yelling that. So anyway, 160 meters is equal to 1/2 times 9.80 meters per second squared times t squared, or t will equal the square root of 2 times 160 meters divided by 9.80 meters per second squared. Unit-wise, under the radical, you would have meters divided by meters per second squared. If you invert that and multiply, you'll end up with, let's see, if I imagine this is a meter over a 1 on top, I'd end up with meters over 1 times seconds squared over meters, which is just seconds squared. But when you take the square root, you get seconds. So unit-wise, we're fine. Okay, I also checked this one out ahead of time. And the time for falling is equal to 5.7 seconds. It took 0.9 seconds before the person finished yelling falling forks to warn people to get out of the way. So the warning time, this isn't an actual physics equation, is going to equal 5.7 seconds minus 0.90 seconds, which ends up being 4.8 seconds. So that's how long people have to get out of the way. Should be plenty of time if they're paying attention. All right. Who would have known in the Pacific Northwest such a thing could happen? Now let's go to the moon. A lunar lander is making its descent to Moon Base 1. The lander descends slowly under the retro thrust of its descent engine. That's an engine that's pushing upward on the lander to slow its descent. The engine is cut off when the lander is 5.29 meters above the surface and has a downward speed of 0.815 meters per second. With the engine cut off, the lander is in free fall. What is the speed of the lander in the instant before it touches the surface? The acceleration due to gravity on the moon is 1.61 meters per second squared. Well, let's draw the moon surface here. There we are, craters all over the place. And here comes the moon lander, which I guess I could stick some feet on this thing. I have no idea how to draw something as complicated as a moon lander. That looks like a three-legged alien, but pretend that it is 5.29 meters from the ground, and that we have, let's see, at the time that its engine's cut off, it's going 0.815 meters per second downward. So this is V naught. Okay, well, let's let y equal 0 down here. And y naught will be 5.29 meters. And I'm going to let up be positive on this problem. Okay, so positive is upward. In that case, our equations look like y equal y naught plus v naught yt minus 1/2 gt squared. V naught y is the 0.815 meters per second, but it's going down. Okay, so let's see, we've got y naught, v naught y equals minus 0.815 meters per second. So we have that as well. We also have v sub y equals v naught y minus gt. So here's what I could do, but I'm going to go an easier way. We know that y is going to equal 0 at the bottom. We know what y naught is. We know what v naught y is. We could solve a quadratic equation for t and then plug it into this equation to figure out the descent, or how fast it's going when it hits the surface. But we can also do this. We can say that I'm going to let v final be the speed at which it hits the bottom. V final squared minus v naught squared is going to equal minus 2g times y final minus y naught. Okay, well, I'll put a y final on this thing right here. That's where it's going to end up. But that's also where y is equal to 0. So That's the kind of origin of my vertical coordinate system. So here's what we have. Y final is 0. Y naught is 5.29 meters. And the acceleration due to gravity on the moon is 1.61 meters per second squared. Next quarter we'll study gravitation, and we'll find out that the acceleration due to gravity on some object, like a spherical object, is equal to g times the mass of the thing you're on, like the mass of the Earth or the mass of the moon, divided by the radius of that object squared. And the moon has a much smaller mass than the Earth does, and what actually determines the acceleration is primarily the mass to radius squared number. And capital G is something called the universal gravitational constant. It's good on the moon, on Mars, on Earth, on Venus. It's good. It's called the universal gravitational constant. So that's how you can figure that out, and that's where little g comes from. But at any rate, here's what we've got. We will have v final squared minus v naught squared is equal to minus 2 times 1.61 meters per second squared times y final is 0 minus 5.29 meters. So in these parentheses we've got minus 5.29 meters, and a minus will make a plus there. V final squared will equal v naught squared plus 2 times 1.61 meters per second squared times 5.29 meters. Okay, v final will be bigger than v naught because we add on this bit here. Okay, one thing about this equation though, it doesn't give you any direction because you know the square of the speed when it hits. Well, in this case, we only care about the speed. Now, we know this thing is going to be on its way down when it hits the moon's surface, but the equation can't tell you that all by itself. We have to use a little bit of our intuition to figure that out. But anyway, if you solve for v final, putting in, let's see, 0.815 meters per second for v naught, you get v final in this case is equal to 4.2 meters per second. And let's see, we have enough information. We should be able to keep 3 sig figs on that. I think so. Let me see here. Looks like 4.21 meters per second. Okay, so there are a few more. There's one more problem that I want to do, but I'm going to save this one for its own video.